So we're going to first look at y equals sine of x. Now, the general form of this equation, y equals sine of x, is y equals a sine of omega x. Meaning that we can put numbers in front of the sign, and that's going to change something about the graph, and we'll go over that. And we can put numbers in front of the x, and that's going to change something about the graph. So before we get into looking at all of the different things that we can change, let's first look at, I guess you could call it the parent graph or the main graph, y equals sine of x, because changing little things in here, or changing one or changing both, is going to change the way that the graph looks. It's going to create transformations. Things are going to go on in the graph. So and let's say that we wanted to proceed like we would if we were graphing a regular function that we had no idea what it looked like. You would make a table. This is going to have to be a pretty big table because sine of x has a lot of different values that we've covered, right? So let's say that I have an x and y table, and does anybody remember the period for sine? How often that it repeats? It repeats every 2 pi, right? All of the trig functions are periodic, but sine, cosine, secant, and cosecant, they all repeat every 2 pi. So that means that its period is 2 pi. So to get the best picture, you would want to plug in every value, including 0 and 2 pi, but every value in between those that are common values. And so that would be all of those places on the unit circle, and that's a lot that we've looked at. But I mean, it's not just too many, it's not super unbearable, but there's a pattern that's going to be followed. And what I'm going to do is I'm going to show you how it graphs, maybe using about how the graph would look using about 6 or 8 points, and then I'll show you the pattern that we can use to help us graph really any type of sine graph. And then I'll add a little bit onto that, a little bit more onto that as we get into more complex graphs. So table, remember, we come up with the x's and we figure out what the y's are equal to. So what I'm going to start with, 0, and then I'm going to write the next points that I'm going to use here. My next x values are going to be those common angle measures from the first quadrant. Now, I'm not going to be using degrees. I rarely use degrees. And I know that's probably what you're used to. So it's okay to convert that over if you need to. But when we start talking about graphs of things, degrees really don't really make that much sense. Even though I've seen them written on graphs, I learned them the way that I learned it in high school. I learned these graphs using degrees. But when you learn that degrees aren't real numbers, it really doesn't make sense to write those degrees down when you're graphing these. So I'm just going to mainly write radians. So what's the next angle measure that's common? It would be 30 degrees or pi over 6. All right, and then 45 degrees or pi over 4. And then 60 degrees or pi over 3. All right, and then what's the next angle measure? What's the quadrantal angle after 60 degrees? we have 90 degrees, which is pi over 2. All right, and I'm going to keep going until I get to pi, and then I'll stop. All right, and so then we need the multiple of what would come next? Would it be 5 pi over 6, or would it be 2 pi over 3? 2 pi over 3 would come next if we're going around the unit circle. And then 3 pi over 4. And then 5 pi over 6. And if I want to stop at pi, that would be the last point I put in my table. Now I have to know what these values are. Alright, so the sine of 0 is what? 0. The sine of pi over 6 is 1/2. The sine of pi over 4 is the square root of 2 over 2. The sine of pi over 3 is square root of 3 over 2. What about the sine of pi over 2? 1. And now these next angle measures, these are all in the second quadrant. Remember, sine is also positive in the second quadrant. So the sine of 2 pi over 3, that's going to be what? Square root of 3 over 2. The sine of 3 pi over 4, square root of 2 over 2. And the sine of 5 pi over 6 is 1/2. And then lastly, the sine of pi is 0. Now notice that all of my y values are positive. So what that tells me is when I graph this thing, at least this part of the graph, when I graph it, all of my values are going to be on the top half of the x-axis, because the top half of the x-axis is where we have positive y values. And I'm trying to make this make sense in, just like if we were graphing any regular old function, we're actually going to figure out where these x's are by using the value for pi that we know. And then sometimes we may even punch in the y, the square root of 2 divided by 2 to see what that's equal to help me graph. Alright? So I'm going to try to space this out as much as possible. So if I want to space this thing out, it's about as far, and it may not be exactly even, or equal, but this here, I guess we'll start here at the origin. This here, this is 0 on the x. Then I'm going to call this point here, or this tick mark here, pi over 2. And then this is going to be pi. This is going to be 3 pi over 2. And this is going to be 2 pi. I'm going to mark off a couple of places on the y. So I'm going to try my best to make this pretty, I guess, pretty much to scale. This is about 1.5, so I might just make my y a little bit bigger than the scale that I have for my x. But we'll say this right here is 1. So if this is 1, you can see the lines on the board. That would make each one of these lines how much? 0.25, right? That would be 0.25, that would be 0.5, that would be 0.75, and that would be 1. Alright, well, I mentioned that pi over 2 was about 1.5. Well, how do I know that? if I go to my calculator and I calculate, I'll say pi divided by 2. So pi divided by 2, I get about 1.57. So, I mean, it is just like the, like you're usually used to putting 1, 2, 3, 4 on the y-axis. Well, pi over 2 is just another way of writing about 1.57. All right. What about pi? We know that's about what? 3.14, right? And that's units, 3.14 units. What about 3 pi over 2? Let's get a guesstimate of that. Pi, or 3 times pi equals, divided by 2 equals about 4.71. And then 2 pi, that's just 2 times pi, delicious pi. That's 6.28. So it's about 6.28. All right. So we want to keep that in mind when we're graphing this so that it makes as much sense as possible. It's just we have points that we're labeling that has, I guess you could say, decimals there. But they're still real numbers. All right. So let's look at the points. So pi over 6 and 1/2. Well, that's the second point. How about the first point? 0, 0. So 0, 0 is the origin. All right, so there we go. And then we have pi over 6 and 1/2. Well, where is pi over 6? It'll be pi divided by 6. So that's 0.52. So that's going to be just a little bit more than halfway. 0.52. Now halfway to where? Halfway to 1. If this is 1.5, so it's going to be about a third of the way to 1.57. 0.5 is about a third of the way to 0.57. How do I know that? Because 0.5 plus 0.5 plus 0.5 is 1.5. All right, so about right here is where I'm going to have pi. Let me write it in a different color. Let's see. Right there, I'm going to have pi over 6. So that's the x value. The y is 1/2. So half of the way would be about right there. That's about half of the way to 1. Okay. The next point is pi over 4. Let's see what that is. Pi divided by 4. So that's 0.78. So, I mean, close to 0.8 or, close to 0.75. 0.75 is about halfway between 0 and 1.5. So about right there, we'll say we have pi over 4. Now at pi over 4, my y value is the square root of 2 over 2. So 2 square root divided by 2 equals 0.707. All right, well, if this is 0.75, then 0.707 is going to be just, really, really close to it, but just underneath it. Okay, so it's going to be about right there. And then pi over 3. Well, pi over 3, pi remembers about 3.14. 3.14 divided by 3 is a little bit more than 1 unit. So if this is 1.5 units, then 1 unit's going to be about 2/3 of the way. I don't know if that makes sense to you. Hopefully it does. Alright, so for pi over 3, we have the square root of 3 over 2. So let's see what that is on the y. 3 square root divided by 2 equals 0.866. So that's definitely going to be above 0.75, and we know that this line right here represents 0.75, so it's going to be on up a little bit more. And then for pi over 2, we have 1. So you see right here where I have pi over 2, we're going to go all the way up to 1. Now, if that was all I graphed and I didn't do a very good job, then I would think that's a straight line if I connected the dots. You know, if I connected those dots, would think that would be a linear graph. All right, but it's a good thing that I took more than just those couple of values, because it's not going to be a straight line. All right, let's see what starts to happen as we go over further on the x-axis. So we have 2 pi over 3. Well, let's see what that is as a decimal. 2 times pi equals, divided by 3 equals a little bit more than 2 units. So remember that pi is about 3.14, and pi over 2 was about 1.5. So a little bit more than 2 is probably going to be about right there, about a third of the way to the next major point that I have written down here. All right, and just to keep me straight, I'm going to put these others on here so I can try to space them out correctly. So I went ahead and labeled just to speed things up just a little bit, because I know for some of you this is so easy it's like pulling teeth, but I'd rather go through this at least one good time. This is going to be 2 pi over 3. This is going to be 3 pi over 4. And this is going to be 5 pi over 6. And if you figure out their decimals, that's about where they'll be on the x-axis. All right, so let's put the appropriate values in for the y so that we can plot those. So for 2 pi over 3, square root of 3 over 3, if you remember when we plugged that in the calculator, that was about 0.866. So we're going to be able to use symmetry here, because remember this one was about 0.866. So this one right here is about 0.866 as well. So it should be symmetric with respect to this point. All right, or form a pattern. Then 3 pi over 4, well, we got square root of 2 over 2 here and square root of 2 over 2 there. Remember, that was about 0.7 something. So that should be a little bit less than 0.75, like this point was. So it should be about the same height as that point. And then 5 pi over 6, we got 1/2. Well, we know exactly where 1/2 is. It's on this line right here. All right, and then at pi, we have 0. Okay, so that should be very symmetric about pi over 2. If you think about this as an imaginary line right here where we have a point, this side and this side are very symmetrical. You could fold them in and they would touch each other. Okay, and so even if when I draw this doesn't look symmetric, it should be. So it's a smooth curve going up and a smooth curve coming down. All right, so I pointed out as we started to graph these points that all of our y values were positive. So with the sine curve between 0 and pi, all of the y values are positive. So what that means is every point is above the x-axis. Now as we get into these other points, these other common points between pi and 3 pi over 2, all those values from the unit circle, and between 3 pi over 2 and 2 pi, remember this is going to be the third quadrant and the fourth quadrant. And if we think about it, if we think back to where sine is positive, remember sine is positive in the first and second quadrants. That's why the graph is above the x-axis. In the third and fourth quadrants, those values are negative for sine. So that means we'll have negative y values to take us down. All right, it's going to be very much like what we just did, except, you know, if I was a math magician and I could take this line right here and just grab it and pull it and flip it down and put it between pi and 2 pi, I'd have that exact same graph down there. So I'm just going to do some guesstimations as to where all of those points are. If I put -1 down here, I think I may have went down 1 too far. Let's see, 1, 2, 3, 4. I went down 2 too far. So there's -1 right there. All right, then I know for sure if I wanted to just do a couple of points, like they're significant points, you see me doing my fingers, significant points. I'm using that term a lot. And the significant point here is 3 pi over 2, because we know the sine of 3 pi over 2 is -1. And we know the sine of 2 pi is what? That's right, 0. So if I was to put those 2 points on there, that'll kind of give me a guideline of where I need to go. Now this graph, of course, doesn't look like this right here. I told you. It's kind of a reflection of this right here. It's going to be smooth going down and smooth coming back up. All right, so that is the graph of y equals sine of x, one complete period of y equals sine of x. Notice that the high point on the graph, the high point for the y is 1, the low point is -1. If you think back to when we went over domain and range, I told you that the range for sine was between -1 and 1 inclusive, meaning it includes those endpoints. Okay? And so remember graphically what the range is. The range is the y values. So every point is between -1 and 1 because the range of sine is from -1 to 1 inclusive. Okay, remember the domain for sine. You can take the sine of anything. So it's going to keep repeating over and over and over in both directions. So if I could like take this and just take this piece of the graph and make a copy of it and pull it over, and where it ends there, if I could put its end right here and draw it again, it would just keep going on and on to the left. And if I could take this graph and just pull it and put the very first point here at 2 pi, and it would keep going on and on and on to the right forever. Okay? So if you ever hear of a graph being sinusoidal, I don't know if you've ever heard of that term. It just means that it has that sine look. And do all graphs have the sine look? No, they don't. But you know as well as I do, cosine's values are kind of similar to sine's values, right? You get some of those same numbers. You'll take when you take the cosine of pi over 6, you don't get 1/2, you get square root of 3 over 2. And when you take the cosine of pi over 3, you don't get square root of 3 over 2, you get 1/2. So cosine must look similar to sine. It just must be shifted around a little bit. And it is. Okay? And that's what we're going to go over now, what the graph of cosine looks like. I'll probably do it a little faster. Probably won't go into as much detail. But just know that everything that I said for sine, as far as all these x values, you can look them up in your calculator. All these y values, you can space it out and try to keep everything as much to scale as possible. All those same properties are going to apply. All right, so that's the basic sine curve. I'm going to show you the basic cosine curve, and then I'm going to show you what happens when we start changing some stuff around in the equation. So, and again, I'm going to go a little faster this time because some of you are starting to yawn and get very, very tired. So I must not be going fast enough. Let's see. So I have y equals cosine of x. So here's my xy table. I'm going to do the same thing that I did before. So I have pi over 6, pi over 4, pi over 3, pi over 2, then 2 pi over 3, 3 pi over 4. My table's starting to look a little crazy. That's okay. 5 pi over 6 and pi. And then let me fill out the values for my y here really quick. These are the same values that some of you wrote down on your test. Notice that when I get to the second quadrant values, you know, before I even write them down, I know that they're all going to be negative, because in the second quadrant, cosine is negative. All right. I'm not going to label every point, but I'll label a couple of these. Let's say that's my high point, that's my low point. Now, cosine, instead of starting at 0, 0, cosine starts at 0, 1. Okay? And then notice what happens. As you go to the right, meaning as your x values get larger, your y values get smaller. Remember, this was 0.866, 0.707, 0.5, 0. So they start to go down, 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 down. Okay? And then these negative values continue. The graph continues to go down, 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 until we get to pi. It's -1. And then what happens if we think about the salty sea chart, when we get to the third quadrant, cosine is still negative, but if you punch the values in, you'll see that they start to go up until we get to 3 pi over 2. The cosine of 3 pi over 2 is 0. And then in the fourth quadrant, the cosine values are positive. Positive values are above the x-axis. So they start to go up, 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 up. Okay? So we connect these dots, or these points, with smooth curves. And that's one complete period for cosine, between 0 and 2 pi. But cosine, its period, remember, is 2 pi as well. It repeats every 2 pi. And it does this in both directions forever. Okay? So if I was able to grab a copy of this and move it over and put this point right there at the starting point, it would continue to the left forever, repeating that over and over and over. And the same if I was able to take a copy of this, and put the starting point here at the end and just keep going on and on forever. So the shape is the same as the sine curve. Really, it's only shifted over a number of units, right? I don't know if you figured that number out or not, but it is shifted over a set number of units. So what happens if we start messing with stuff? If we start putting other things in the equation? We start changing the number in front of the trig function. We start changing the number in front of the x here. You know, both of these have, even though we don't write it for sine or cosine, they both have a 1 in front of the trig function, and they both have a 1 in front of the x. And so that gives us the basic sine and cosine curve. Now, if we change the value in front of the trig function, this is for sine or cosine. So if we change this a right here, and I'll tell you what that stands for in just a second. But if we change the a, then that's going to change the high point and the low point. Okay? So if we have y equals a sine of omega x, or y equals a cosine of omega x, changing the a changes the high point and the low point. So what does that mean? That means that this a right here stands for, anybody know? Yeah, amplitude. The way that we calculate the amplitude is by taking the absolute value of a. So when you take the absolute value of whatever is in front of the trig function, that gives you the altitude, the amplitude. I guess you could think of it like altitude, but the amplitude of the trig function. Okay? So let's say that I had y equals 3 cosine x. And I'm not going to draw this all the way out, but let's say that this graph that I'm about to put up here, let's say that is y equals cosine of x. Then y equals 3 cosine of x. Instead of having a high point of 1, it's going to have a high point of 3. And instead of having a low point of -1, it's going to have a low point of -3. It's still going to cross at the same places on the x-axis. Okay, it's just going to have, ooh, that wasn't too good. It's just going to have a higher point 3 units up and a lower point 3 units down instead of 1 each way. And that's the same for sine or for cosine. Changing the amplitude is going to change the height, or the high point and the low point to that number. Now, if for some reason, let's say we wanted to look at the graph of y equals -2 sine of x. Well, the amplitude here is equal to the absolute value of -2, which is 2. So that is going to change the high point and low point to 2. However, if you have a negative in front, that's going to flip the graph. So what do I mean by flip the graph? I mean that, let's say, so I'm gonna graph really quick. This is y equals sine of x again. So let's say it looks something like this. That's y equals sine of x. Then y equals negative 2 sine of x. It will still have a high point of 2 and a low point of negative 2, like you would think it would. Oh, that's positive up there. That's positive 2, it's negative 2. The thing is, though, instead of the high point coming first, the low point will come first. It's still going to cross the axis in the same places because it's still going to be equal to 0 in the same places. It's just that where we had a high point before, we'll now have a low point. Where we had a low point before, we'll now have a high point. So this graph it's still going to start here, then it's going to go down, then up, then back down. So if I take away y equals sine of x like that, there's y equals negative 2 sine of x. So negatives in front of every trig function actually will flip the graphs. Now, changing the amplitude of the trig functions doesn't always do the same thing. Changing the amplitude for sine and cosine changes the heights. It makes your high point and low point whatever that number is that we get for the amplitude. Now, if we start changing the number in front of the x, so in my formula, it looks like a W, but we're going to call it omega. So changing the omega in front of the graph, that's actually going to either shrink or stretch the graph. Okay, when I say shrink or stretch, I guess I'm talking more about stretch or compress. So if the number in front of the x is greater than 1, then think about what you're doing to those values. Instead of taking the sine of pi over 6, you're taking the sine of 2 times pi over 6. So you're taking the sine of pi over 3. So it means it's going to go up a lot faster, it's going to go down a lot faster, so it's going to be compressed. So whenever the omega, the number in front of x, whenever that is larger than 1, that's going to compress the graph. Whenever the omega, or the number in front of the x, is less than 1, that's going to stretch the graph. Okay? Just to show you a really good picture of that so that you can see what I'm talking about. There is a method to doing it, and I'm going to teach you that method, but I would rather you understand the concept before I show you actually how to graph it. So here is the graph that we went over. This is the copy from the book. I'm on around page 147 of your ebook. So here's the graph y equals sine of x. Alright, and here is the graph of y equals 3 sine of x. Well, no, that's not what I wanted. 3 sine of x would just be taller. Here is the graph of... That wasn't what I wanted. That'll be okay. Here's the graph of y equals negative sine of x. So let's look at that real quick. See if we can compare the two. I know one is larger than the other. Maybe I can stretch it out just a little bit. Try to get it to look a little similar. And again, that is y equals negative sine of x. So they're the same graph. One's, of course, a little thicker than the other, so it does make it look a little different. But if we were to take and flip this graph down and, flip this part of the graph up, if I was able to do that, then that would be the same graph. And then here's y equals negative of sine of 2x. All right, we are a little limited here. I think I can go to a trig window. There, zoom trig. So let me show you what, according to this graphing utility, come on, there it went. Here's y equals sine of x. Now let's see what y equals 3 sine of x would do. So this is one complete period. That's what we graphed earlier. So here's y equals sine of 3x. So while it takes 2 pi to go up, down, cross the axis, go down, down, come back up, for y equals sine of 3x, look at this, up, down, up. So right here where my cursor is, that's where the period for the second graph stops. That's one complete period. So the bigger the number here, the more compressed, if you think about it like a spring, the more compressed the graph becomes. The bigger the number in front of the x. The smaller the number in front of the x, so let's say that I wanted to, instead of graphing sine of 3x, let's say I wanted to look at 4 sine of x. So that doesn't change like the compression, that just changes the height, right? Well, what if I wanted this to be sine of 0.25x? That stretches the blue graph out so far that it almost looks like a straight line. But if I zoom out, you can tell now that this goes up, down, up, down. It's just a lot slower. One period here is actually 8 pi. And I'll show you how to calculate all of that. All right. So changing the amplitude is going to change the height, the high points and low points. Changing the number in front of the x is either going to compress or stretch the graph. But what is that really, how do we know how to graph it then? Well, there is a way to figure out how to graph this by just using significant points. So significant points for sine and cosine are places where the graph either crosses the axis or has a high point or low point. So this is y equals sine of x. Here's the first significant point for our graph. Here's the next significant point at pi over 2 and 1. Here's the next significant point at pi 0. Here's the next significant point at 3 pi over 2 negative 1. And then this would be the last significant point, 2 pi and 0. So if I have those 1, 2, 3, 4, those 5 points, I guess, then I know if I follow the pattern of sine goes up, then at the next significant point we have a high point. Then at the next significant point we cross. Then at the next significant point we have a low point, and at the last significant point we cross. Let me go back through that again. For sine, at the first significant point, that's where you start. You start sine at 0, 0. At the next significant point, you have a high point. At the next significant point, you cross. At the next significant point, you have a low point. And at the last significant point, you cross. That will always give us the shape of the sine curve if we follow that. Start, go up, go down and cross, have a low point, come back up. No matter what these x values are, if we remember this basic shape of the sine curve and we label our axis the way that we need to label it, then we'll have a graph of the sine curve. And changing the number in front of the x is going to change those significant points. It's at least going to change the x values. And I'll show you how to figure all of that out. Okay, so don't worry, I'm going to show you. I know some of you are shaking, you're scared, but don't be scared. I'm here for you. All right. I've already shown you how to find the amplitude, right? So amplitude is always going to be, in that general form, the absolute value of A. Now, the period, the variable that we use for period is T, capital T. I have no idea why. I've probably been told before. It probably was not discovered or thought about in English, if I had to guess, and that T probably stands for some other word, probably French or German. But period is going to be T. Now, for sine and for cosine, one complete period for the sine graph or cosine graph, if it's just 1x, was 2 pi, right? So the way that changes, if you have a different number in for your omega, it's going to be 2 pi divided by omega. All right, so that's for sine or for cosine. So let's say that I had y equals 5 sine of 3x. I'm not going to graph this yet. Let's work on identifying the amplitude and the period. So what would the amplitude be equal to? All right, so amplitude would be the amplitude, I'll use an abbreviation, AMP. All right, amplitude is going to be the absolute value of 5, which equals 5. All right, the period is going to equal, that's the variable t, which is going to be 2 pi divided by 3. Right? It's 2 pi divided by whatever's in front of x. Now, there's nothing that I need to do to simplify that. That is simply 2 pi over 3. So the period, one complete period for this graph, would be 2 pi over 3 units long. That's the length on the x-axis. If I had a ruler and I was able to to rule it. I was able to measure it. It would be 2 pi over 3 units long. Everything we had on that graph where it touched, it went up, it came back down, it went back up, all that, if you were to measure it, would be 2 pi over 3 units long. All right. Let's look at another one. Let's find the amplitude and period if we have y equals negative 2/3 cosine of 1/4 x. Alright, so first the amplitude. So what's the amplitude? 2/3. Alright, what's the period? Two pi divided by, alright, whatever's in front of the x. So 1/4. Flip and multiply, you get what? 8 pi. Alright, if you flip the fraction and multiply, you get 8 pi. Alright, what about this one? Y equals 6 sine of pi x. Alright, so the amplitude is 6. The period is 2 pi divided by what? Pi. That's the number. Pi's a number. It's very yummy, but it is a number. It's in front of x. So, what do you think would simplify here? The pi's cancel out. My period would be 2. 2 what? 2 units. So, it doesn't matter what the units are on the graph. If I was to look at the graph of this thing, guaranteed the entire graph would be 2 units long. One complete period would be 2 units long. This is the real number 2. You know, I know that we deal with radians a lot, so we don't really know what numbers they are, and none of them are exact, but this would be 2 units on the x-axis. That would be the distance. That would be the from start to finish of the graph. All right. You do this one. Give you 2 tricky ones. Let's see. Y equals 4/3 cosine of 3/4 x. And the super tricky one. I'm so nice that I'll do the amplitude on these. I'll just get you to do the period. How about that? You're supposed to say, wait, that's the hard part. Let's switch. So the first problem should be pretty straightforward. The second one's kind of tricky. So if you're working on the second one, you might want to hold off on that. All right, the first one, let's see. That's going to be 2 pi divided by 3/4. So flip and multiply, and you get what? 8 pi over 3. So 8 over 3 times pi, or 8 pi over 3. Now the reason why I said this one's a little tricky, I know I'd already written something down and technically it was wrong. Because remember, what do we do if we have a negative right here? Is there some kind of even odd property for sine? Wouldn't there a property that says the sine of negative theta is equal to the negative of the sine of theta? So if you have a negative right here, you need to take that negative and move it to the front, right there. So the amplitude is going to be the absolute value of negative 5/3, which is still 5/3. I have to move that negative though, because remember, a period is a distance. It's a length. And if I try to calculate my period and plug in that negative value, then I can't have a negative length. You can't measure out a negative length. Alright, it's still kind of tricky because of the way it's written. That's 2 pi divided by 2 pi over 3. Now you don't say 2 pi divided by 2 pi. Alright, don't work like that. This is a fraction. So I want to flip this fraction and multiply. So when I do that, I'm going to have 2 pi times, what's that going to become? 3 over 2 pi. Right? If you flip that and multiply, now if you think about that like it's over 1, those cancel out, and what's my period equal to? 3. Okay.